Moderator, our distinguished speaker, Dr. Atia and Dr. Ouyang. Today, I'm very honored to be invited as a speaker in this conference. Unfortunately, due to a sudden military service call, I'm unable to attend in person. If you have any question, please don't hesitate to contact me. I truly hope to have the chance to connect and exchange ideas with all of you. To start my talk, I would like to introduce some change in scientific research in the AI era. In the past, drug research needed high-throughput screen to test millions of compounds to see if they were useful, which took a lot of time to search each option. With the help of the AI, we can predict potential compound combination, which greatly reduced the search space and speed up the whole process. Similarly, in exploring medical technology, we also have millions of examination and disease connection to search. For example, we might want to know if ECG can be used to detect low ejection fraction or paroxysmal atrial fibrillation. Now AI models have reached the level of human expert. AI can search the connection in large labeled database. We only need the AI model to run tests and tell us which examination and disease connection have high accuracy. This can help us create a lot of new medical knowledge and give all examination new value. For the past few years, I have been doing research in AI ECG. I would like to introduce an important scholar in this field, our distinguished speaker, Dr. Atia. In 2019, Dr. Atia and his team published a study in Nature Medicine. They were first to report that ECG can be used to detect the low ejection fraction, which was not recorded in textbook before. Later, their team published another study in The Lancet, showing that they could detect high-risk patients for paroxysmal atrial fibrillation from ECG during sinus rhythm. A few years later, thanks to the work of Dr. Atia's team, we now know that ECG can also identify many other heart diseases. It is hard to imagine before the AI era. The next question is how can we use this new medical knowledge? Dr. Atia's team have given a good answer using AI ECG for opportunistic screening. In this study, after patient received an ECG, it was automatically analyzed by AI. If the AI found that a patient had a high risk of low ejection fraction, it will alarm the doctor in the EHR. For the positive subgroup, the intervention group received more echocardiograms than the control group because the AI alert, which helped find more cases of low ejection fraction. This approach of using AI alert to prompt further testing for high-risk patients could improve patient outcomes. In our recent study, we used AI ECG to identify high-risk patients for sudden cardiac death in the hospital. Similar to the previous study, when the AI identifies high-risk patients, the AI system will automatically notify the attending physicians. The attending physician is then fully assessing the patient's condition and providing the appropriate intervention. In the end, we found that the AI ECG alert reduced the 90-day all-cause mortality rate by 31% for high-risk patients. This study clearly shows how AI has improved healthcare quality in the past few years. Using AI to discover new medical knowledge has a serious limitation. AI needs a lot of sample size to show enough accuracy. However, many times we don't have enough samples, especially for rare diseases. For example, our hospital has fewer than 300 cases of hypertrophic cardiomyopathy and fewer than 40 cases of digoxin toxicity. This makes it very difficult to train AI model for us. If you have enough sample, everything will change. For example, Mayo Clinic have more than 3,000 cases of hypertrophy cardiomyopathy, which allows them to train an AI ECG model that reached an AUC of 96%. The problem of not having enough samples happens in almost all AI model development, especially in natural language process in few years ago. In the past, it was almost impossible to image AI having conversation ability, but now I'm sure many of you have used ChatGPT, which has become a part of daily work. How was such a powerful model trained? There are two main steps. The first step is using sentences from the internet to learn language meaning, which created a pre-trained model, often called a foundation model. Then, in the second step, a small part of question and answer pair are used to fine-tune the foundation model. This process gives the model an expressive conversation ability. You can imagine that collecting question and answer pairs is very costly, so the success of large language model depends on having a strong foundation model rather than on created a huge question and answer database. How can we use foundation model in the medical field? Let's start with language models. This study is a paper by the New York University team published in Nature. Similar to ChatGPT's training strategy, the first stage of this paper is pre-training on EHR data. In this stage, a few words in sentence are randomly masked, and the AI model must fill the correct words. In the second stage, text-specific fine-tuning is done on top of the foundation model. The output of a deep learning model is usually a set of meaningful high-level features, which we can call it embeddings. Using these embeddings, we can directly predict diseases or clinical events. In this study, they use this EHR-based large language model for 5 different tasks. I want to highlight its prediction of in-hospital mortality. Just using the admission note, it achieved an AUC of 95%, which is much higher than the 0.85 to 90% range seen in AI ECG. We can expect a great value from this model in the future. Let me introduce the experiment result to show the power of the foundation model. This figure compares the accuracy of different AI training strategies with different sample size. The model with pre-training showed a 5% AUC improvement compared to the model without pre-training process in the same number of samples. This improvement is especially strong when the fine-tuning sample size is small, such as when there are only 1,000 samples for fine-tuning. Let me introduce the field of AI ECG, which I have been researching for the past few years. The paper from Mount Sinai Hospital also shows the power of foundation models. Although ECG are input as images into the AI model, the pre-training strategy is similar to that used in language task. It involved masking small patches in an image and having the AI model fill in missing parts. The foundation model, trained in this way, is then used for predicting multiple diseases. Let's choose one of the tasks using AI ECG to detect low ejection fraction as an example. Similarly, we can see that the model with pre-training shows more than 4% AUC improvement compared to the model without pre-training in the same number of samples. This improvement is especially strong when the fine-tuning sample size is small. For example, when only 1% sample are used in fine-tuning, the AUC difference reaches 13%. In addition to unsupervised learning method we just discussed, which is based on a mass prediction, I'd like to introduce a more useful pre-training method in the medical field. This method, developed by OpenAI, is called CLIP. The full name is Contractive Language Image Pre-training. The pre-training method requires that each image has a corresponding text description, and the goal is for a model identify the correct image description pair. A model trained by this way has an amazing ability called zero-shot prediction, which means it can make predictions without any fine-tuning samples. Look at the image at the right. We can try giving the same prompt, like a photo of something, and then replace something with different object, like plane, car, or dog. The AI model can then evaluate which description is most likely to match the image. I would like to introduce the work conducted by our distinguished speaker, Dr. Ouyang. He applied the CLIP model to interpret echocardiogram. Since echocardiogram usually has a corresponding doctor reports, it is not hard to get image description pair. Dr. Ouyang's team used this data for pre-training. This study found that zero-shot prediction has impressive accuracy in predicting low ejection fraction value and shows consistently high accuracy in external radiation. This research clearly demonstrates the potential of CLIP model in medical field, as image description pairs are easy to get from EHRs. You might wonder why we don't just train a language model that can look at pictures and text instead of using the CLIP model. This is because the CLIP model uses sample 12 times more efficiency than language model trained to describe image, making it the main method for self-supervised training today. Additionally, I want to highlight that while CLIP's zero-shot prediction ability is very impressive, I believe its great strength is its better fine-tuning ability with small sample size compared to other unsupervised learning processes. For example, as shown in the image on the right, fine-tuning with just 4 samples per label can reach the accuracy of zero-shot prediction, and more samples lead to even higher accuracy. In the medical field, I believe accuracy is more important, so our team is focusing on exploring CLIP's few-shot prediction ability. We have already trained a CLIP model using CXR report pairs. After pre-training, we kept all the AI model's parameters fixed and used only linear probing to predict diseases. This study used 1 million samples for training. Here are the results. We can see the purple line shows the accuracy based on the CLIP model pre-training strategy, while the green line shows the accuracy of a traditional convolutional neural network. Using CLIP model's pre-training strategy with linear probing, and with only 128 cases and 384 controls, we achieved an average AUC of 90% on radiology tests, which is similar to the convolutional neural network trained with 1 million samples. The results of echocardiogram's label were similar. This result once again highlights the power of pre-training foundation models. We are integrating the data from the old military hospital in Taiwan to train a multi-modality foundation model involving more than 10 million patients. This model will be able to use data from Taiwanese Healthy Bank data as input and expect to predict any diseases in the future. Of course, we are very interested in seeking collaboration opportunities to join train this foundation model. I believe this will be the main training strategy for the next generation of medical AI. In the future, AI will play an important role in the next generation of healthy care. After people visit a hospital or clinic, frontline doctor will identify serious diseases, and the medical record will be reanalyzed by AI. Through opportunistic screening, AI will help identify potential underdiagnosis conditions. Although current discriminative AI models have the potential to improve care quality with new medical knowledge, today they can only cover a limited number of diseases. Once foundation models are developed, there will be a huge chance, and this is the vision I have for the next generation healthcare system. Here's my take-home message. AI model can create new medical knowledge through big data, which will create new ways of using old examination. Foundation model has potential to resolve healthcare problems by providing advanced diagnostic support, prognosis, prediction, and treatment recommendation. We need to train a multi-modality foundation model and introduce AI-enabled opportunity screening for the next generation healthcare system.